Hello everybody, I'm Tom Wysmuller. As you can see, the subject is sea level rise. It's a water conference, and the oceans have a lot of water. And some people think it's rising, and they're right. And some people think it's falling, and they're right too. So I'm going to talk about what's real and how it works. Now you notice there are a couple of ways to measure sea level. Tide gauges and satellites. They are all linear in nature, and yet they point in different directions. So there's something wrong here. We're going to try to resolve what's wrong. And we're going to take a good hard look at the effect of CO2 on sea level. So let's see if I can get this working right. This is what people say is the future of New York City. Well, guess what? You're not going to see this in your lifetime or in anybody else's. This happens to be the cover of a book by Heidi Cullum, a meteorologist who's making a fair amount of money on this book because it scares people. But it's not going to happen. This is where the water in the oceans recently really came from. This is the great Laurentide Retreat. And if you notice, the Laurentide is an ice sheet that covered North America with 1 and 2 miles of water, sometimes almost up to 5 kilometers of water depth. That's a huge amount of water. Now you notice this is years ago. The sheet is retreating and advancing. This is the continental shelf of what will become the United States, not the United States. And now the Lake Bonneville has disappeared. And the ice sheet goes, and the oceans are flooded with water, and when the sheet finally disappears, we have the current day coastline of America and Alaska. This is what it looked like on a graph. Around 22,000 years ago, sea level started rising. There's not a lot of information. By the way, here's the peak of the last interglacial. Then as the ice built up, the sea level dropped, because that's where the water came from. So here we have a stretch. What I like to do is stretch this across the entire graphic. And it looks like this. This is just the last 18,000 years. And you notice between these two arrows here is the greatest increase in sea level. Here's one pulse that resulted in almost 80 meters of sea level rise within 500 to 1,000 years. How did that happen? Well, it happened when this lake here, Lake Bonneville, decided to break through and run down the Snake River, and this is what was left. These are rocks that you see that were rolled down the Snake River. There are thousands of these rocks. The lake dumped out, and again, it's a huge lake. The Great Salt Lake now is this little thing right here, and flooded the ocean, and that created this great meltwater pulse that you see here. Let's see if I can zip along here a little bit. This is the proposed Ipcc sea level rise pathways. They are representative pathways that point to a 1 meter sea level rise if CO2 emissions continue as they are. If CO2 is attenuated, the Ipcc says we're only going to get 0.2 of a meter rise. Well, the Americans wanted to outdo the Ipcc, so this is the National Climate Assessment. They're saying that we're going to have 2 meters of sea level rise by the end of the century. Even the lowest pathway, representative pathway, is twice the recorded sea level rise in the last 100 years. And they're all based on CO2 increasing. Later on we'll see if that connection makes sense or not. This is Jim Hansen, who in 1998 predicted a very rapid sea level rise. It didn't happen. So in 2007 he makes this chart which shows a logarithmic doubling. So he's saying the last 20 years of the century, we're going to get 4 meters of sea level rise. I don't know where that ice is coming from. And again, the Laurentide sheet is gone. So here we have 3 different sources to measure sea level rise. They are all linear, every one of them. The tide gauges, the satellites, and the European Envisat satellite. Well, how can they be different? I mean, this is almost more than double the tide gauges, and the tide gauges aren't accurate either. And I'll explain why. Here's what a tide gauge looks like. Here's the gauge, there's instrumentation. It is actually grounded in the local bedrock. So it's not tied to this dock. If the dock goes up and down, the tide gauge doesn't. This happens to be in Portsmouth, New Hampshire. There are tide gauges all over the world. The black ones are the ones that have been there longest. You notice the most tide gauges are in the places where land is sinking. Those people there are very concerned about sea level rise. Where land is rising, like up here, and it's rising because the glacial ice sheets have left. So the land itself rises because that giant weight has been taken off them. Not too many tide gauges up here where the land is rising. These are local effects. So this is a tide gauge from New York City. And you notice a fairly steady upward rise. Well, during the same period, this is from 1875 on, New York City started building many, many buildings. If you've been to New York City, you've seen the skyscrapers. And by the way, they're not light, they're very heavy. They rest on bedrock. However, the bedrock rests on something called the asthenosphere, which then rests upon the magma. And it slowly, slowly sinks in a steady way. How do you know it's sinking? 25 miles away in Port Jefferson, New York, the tide gauge shows there's very little rise. So they're not building any buildings in Port Jeff. Same thing up in Boston. After 1961, which is right here, Boston put up 19 new skyscrapers, large, big, heavy buildings, and they have what they call frangible bedrock. It's not even as solid as Manhattan. Portsmouth, New Hampshire, 50 miles up the coast, no rise whatsoever. Maine, Portland, Maine, is tectonically inert, which means it's neither rising nor falling. The sea level in Maine today is identical to the millimeter as what it was in 1947. The old timers in Maine say sea level ain't going up, and they're right. This is a really good way to look at it. This is by the great Axel Mørner, a sea level expert from Scandinavia. And Mørner says, you have to look at it realistically. This is all of the United States 159 tide gauge stations. In some areas, the land is rising. You have uplift. So you actually have a sea level drop. And then you have subsidence, which is actually more of the stations, where sea level, the east coast of the US, the southern east coast is falling, and so is the Texas coast. There you have a rise. He says the way to judge real sea level rise is in this center, the places where there is really no movement up or down. And NOAA did this on a world scale. And you notice the cross point here, these are all the stations where land is sinking. And these are the stations where land is rising. So if you average all the stations, it looks like sea level is rising more than it really is. And that's exactly the statistics. That's why the tide gauges aren't that accurate. The average is actually less than the 1.7 that the total average of tide gauges shows. And here are satellites. The satellites are the great promise. Satellites should really work well. Why? Because they fly over the ocean, they have microwaves. The problem with satellite, you notice here the sea surface is a little bit wavy. If you have a radar that hits a wave that's angled like this, the radar bounces off and doesn't return to the satellite. So what you have to do is increase the footprint of what you're measuring. That changes some of the geometry involved in the measurements. The other real problem, well, first I want to show you that it's not that easy to measure this ocean surface. I'm going to put this in motion. Where you see red is where you have sea level actually higher than normal, and where you see blue, it's actually lower. If you have a high pressure system over the ocean, it depresses the ocean. If you have a storm like a hurricane, it lifts the ocean up. Now I need to put this in motion too. How do I do that? get down to the bottom here somewhere. Is it working? Yeah, there we go. And now you see that the sea level is actually changing as time passes. I'm going to do one almost complete rotation of the globe here. Here we have some storms off the coast of Japan, low pressure system, bulge up the ocean, and it rises. We're going to get the same in the Indian Ocean. Take a look at the thermal expansion of the Red Sea. It bulges up. By the way, this is 100 times the actual rise, what it shows. So the Red Sea heating up by expansion goes up. Now we're going to get into the Atlantic Ocean. I'm going to wait till the world turns around because someone had an El Nino, La Nina question, and you're going to see La Nina very clearly in a minute. So here you have a La Nina forming, a heavy La Nina, because it's going to turn very, very red here. This should be red. And that means the tropical Pacific is cooling. Here you have El Nino showing up. El Nino means it's warming, so the ocean is depressed. This is what La Nina looks like. Lots of clouds over the Pacific, reflecting sunlight. There are thunderstorms. They lift up the ocean, and the albedo of the storms themselves gets reflected off the Earth at wavelengths that CO2 cannot intercept. So if you have a lot of cloud and a lot of snow, it has to get colder. Let's see. This is the adjusted satellite. Now, by the way, I've left the seasonal signals are in, and you see it goes up and down with the seasons. I'll explain why in a minute. But you notice it is also very linear. I want you to notice the two spikes above the arrows. There's a huge spike here in sea level rise, 1997-98, an enormous spike. And there's also a 2-year spike here in 2011-2012, huge upward spikes. Later on, you'll see why we have those spikes. Here's the problem with satellites. They don't have the resolution to measure what they're measuring. We're measuring sea level in 1 millimeter or 2 millimeters a year. The best the radars can do is 23 millimeters. It's, and the C-band is even worse, 56. What's worse, we don't even know where the satellites are. The orbital tracking error is between 20 and 40 millimeters. So how are you going to measure a 1 or 2 millimeter rise? It's like taking a meter stick like this, which is blank, and trying to measure this little block accurately. Well, how do you do that? Well, what they do is they measure it 6,000 times and hope they get it right by averaging. Here's a better satellite. This is the NVSat. And NVSat is a flying boxcar. It was the latest European satellite. This is what it looked like in the lab. Now we have real good accuracy from NVSat. The little dots show the sea level rise. You notice there is a 2 centimeter difference seasonally. Now, by the way, you can't really see the lines here, but each of these peaks happens to be in January, or actually January to February. Now, why is that? Well, first of all, the sun heats up the oceans, and you have thermal expansion in the oceans. At that time of year, this is what the satellite sees. It's almost all ocean, because it flies over the southern hemisphere in its winter. And down here, this is where it flies over the northern hemisphere. And the satellite doesn't fly there, the sun shines there. So the sun shines here, you have lots of thermal expansion in the ocean, and it shows up. This is what the comparison between the Jason Topek's Poseidon satellites and NVSat. And NVSat, you notice, is only showing about a 0.5 millimeter sea level rise per year over the 10-year periods it flew. While the American satellites and other French satellites are showing 3 millimeters. Well, there's something wrong there. Then they tried to correct the NVSat data to match the American satellites. They came close. Here's the resolution they had to figure out how to resolve that 2.6 millimeter difference. They didn't quite succeed. Remember those 2 years I talked about? The 1997-98 and 2011 and 2012, where we had the huge spikes in sea level rise. Well, they happened to coincide with the spikes of the sunspots in the 11-year cycle. So why would a sea level rise occur in a peak of sunspot activity? Well, for one thing, what the sun does during its high periods of sunspot activity is it bubbles and expands the atmosphere of the Earth. And the satellites, they don't fly in space. They fly in the upper reaches of the atmosphere. And when you're in the upper reaches of the atmosphere and the atmosphere balloons out, you get more particles of atmosphere. And this is what it looks like. This is Brownian motion. These happen to be 2-micron particles suspended in water, but space looks that way too. When you balloon the atmosphere up, you get more of these particles hitting the spacecraft. Each one slowly slows down the spacecraft. If you slow down the spacecraft drops. If we can't figure out where the spacecraft is, we just assume, oh, must be measuring sea level. It's not, it's measuring satellite drop. And that's one of the keys. And this is how you figure it out. What you do is you do a transit test. At each year, you see where the satellite crosses a certain line where a certain star exists. If the satellite shows up a little bit early and goes ahead, that means it is lower in altitude. They're doing these transit tests now. I have not seen the results. I suspect you're going to see that the satellites have dropped slightly in orbit. This is a more accurate way to find where the satellite is than the radar that they're using. Now here we're going to talk about temperature and CO2. From 1880 to now, we've had a huge rise in CO2. This is where the industrial age started pouring CO2 into the atmosphere. Is there a correlation between CO2 and temperature? Well, for the first couple of years, the temperature is dropping here even as CO2 goes up. And then finally, CO2 correlates very, very nicely with temperature as it goes up, but only for 2/3 of the way over this 135-year period. This graphic came from that same national climate assessment that the Obama administration put out. Is this the whole story? It really isn't. I'm going to go back now 2,000 years. And this will be a small subset of the 2,000-year period. Here's 2,000 years. Here's a little subset right underneath this arrow here. This is the graphic you just saw up here. And it's here. So here the temperature drops and goes up. CO2 for 2,000 years has been flat, absolutely flat. The medieval warm period skyrocketed temperatures. The little ice age, they plunged. And now finally here, as the industrial age begins, CO2 goes up. Finally, CO2 looks like it's correlating with temperature. But what happened back here? Nothing. We actually have a 4.5% correlation over that 2,000-year period, which really, really is not any linkage worth talking about. How about sea level during that same period? Sea level, once the Laurentide ice sheet melted here, sea level has been relatively flat. At the same time, that CO2 has been flat. But there's not a lot of relationship there between CO2 and sea level. This is what the CO2 graphic looks like. This is the Mauna Loa. This is northern hemisphere carbon dioxide data. And it's seasonal. This is April, and this is October. You notice CO2 rises until April. What happens in April? The trees get leaves, the grass grows greener, and the plants suck in carbon dioxide. Carbon dioxide drops. Each of these is a drop, a seasonal drop, and then a rise. And you notice almost every one of these rises is higher than the other. So the CO2 is increasing on a year-to-year basis. Not every year. If you look back here, you see a little drop. Here's why it dropped. You have Agung. Agung is a big volcano in Indonesia, and CO2 actually dropped for a 3-year period here. But I'm going to take a subset right here, which is more before Agung, the average rise, and I'm going to show you what it looks like. But first I want to I'm going to show you this graphic here. This is from the Ipcc, and this is going to need some time to explain what's going on. This shows the 3 different greenhouse gases, carbon dioxide, methane, and nitrous oxide. And you see the CO2 totally overwhelms methane. Even though methane is more heat trapping, about 20 to 23 times more heat trapping, CO2 gets overwhelms it. 770 billion metric tons of CO2 gets added to the atmosphere every year. Humans add 23 billion metric tons. Not a lot in comparison. So here's the percentages. Natural, 97%. Human, 3%. The total is 100%. The reabsorption is 98.5%. How do you reabsorb? Well, reabsorption means the plants are sucking it in and the ocean is sucking it in. The ocean absorbs and releases all the time. The warmer the ocean gets, the more it releases, because as the molecular motion in the oceans increases, it kicks out the heavier CO2 molecules. This is how it looks graphically, and it's not that easy to see on this graphic here. Here's where the base is, and you go up here, and I'm going to drop again into October, and you notice this little dot is higher. That is the annual difference. The annual difference is 11.7 billion metric tons. I don't know if you can all see that in the back. The annual absorption and reabsorption is 793. So the 11.7 is what we've added each year. This is a better way of looking at it. You notice I'm going from one top here to the next. And the thin blue, the blue line here is the 11.7 billion metric tons. The darker blue line are the most ambitious targets of reduction of CO2 that they're counting on as a result of the upcoming Paris conference. So we're talking about 400 million metric tons, but it's 3.4% of the 11 billion increase per year. So we're not even getting the total increase. Now, this is the sea level rise chart of Wysmuller, Germany. Now, why did I pick Wysmuller? Wysmuller happens to be in the Mecklenburg Bend in the Baltic Sea. And Norway is rising because the giant ice sheets have lifted it and are actually have left it and are lifting the Norwegian coast. Holland and Belgium are sinking because they're on the opposite end of that seesaw. Wysmuller is right in the middle. So Wysmuller shows you the average not tectonically affected sea level rise per year. It is a very simple straight line. We've had a massive 38% increase in CO2 since 1880, since this graphic starts here. Is there any sign that you see of an acceleration of sea level rise in a tectonically inert part of the globe? I don't see any. Zero. We've had this huge increase in CO2 and no sign of acceleration whatsoever. If there's no sign of acceleration, if you increase it by 38%, if you reduce it by less than the annual increase, you're not going to see a signal either. So here's an increase in CO2. And my final question is, can the Paris proposals to reduce CO2 have any effect at all on sea level rise? There is no instrument that exists that could measure that. Even if we decided to shut down all of our electrical use, stop all the cars from running, close every factory, we would be able to reduce the annual CO2 by a little bit less than 1.5%. We can't measure that difference, even if we shut down everything. CO2 and sea level rise are just not linked. Thank you, folks.
Thank you very much. You still have left a couple of minutes, so
yeah, I tried to cut it short. So
yeah, you made up a little bit of time. So I'm quite sure there are several questions. So should we start with the break in between with Jacob, or should we keep that for later on? Leave it. Okay. I move to the back and then move over there.
My question is about, in the beginning of the presentation, you spoke about very rapid sea rise. and that it was due to the glacial lake.
Not the glacial lake. It was due to the entire disappearance of the Laurentide ice sheet. Now that lake happened to represent a spike in the sea level rise.
But straight afterwards, I mean, the deep freeze followed. So what do you think caused both the melting of the ice and then afterwards the deep freeze?
You're talking about the Little Ice Age?
The Yangatwa period, yes.
Yes, the Little Ice Age built up some mountain glaciers in Europe. It did not create an ice sheet miles and miles thick in the, in North America or the rest of the world. It was a 200-year downward spike. The growing of the Laurentide ice sheet took place over more than 100,000-year period. There's a huge difference. Now, had it stayed cold in the Little Ice Age for the next 50, 60,000 years, yes, you would have built up enough glaciers to reduce the sea level. But the Little Ice Age just was too darn short. Yeah, you got to speak in the microphone.
Yeah, the microphone's not working properly. Okay. So I was just wondering about something that you said earlier about the sunspots of 2012. It was supposed to have been a solar maximum.
That's correct.
That's what we were expecting, but that's not actually what happened. It was actually quite a quiet year for sunspots. So how can it have shown that correlation that you talked about?
Okay, let me get back to that graphic, all right?
It was totally unexpected.
Now, the fact is that the 2012 max was half the size of the previous one, but it was still a max. And there was still a rapid increase in sunspot activity up to that point. Remember, the sea level drop that was recorded on the sea level graphic was in this period. It wasn't at the peak period, but it was as it rose. So those two coincide very nicely.
It was actually very, very quiet though.
Well, it's not quiet. This is half the number of sunspots that you would have expected. It should have, actually, it's only two-thirds. The max here is about 150, and the max here turned out to be 100 in 2012. It was definitely the most quiet period of a maximum in many, many years. So yes, sir.
Yeah. Just as a point of comment, you might remember when we were studying in the university that Jim Hansen was proposing the global ice age theory very emphatically.
Well, he changed his mind, and in 1988 he testified in front of Congress, and it was. There's more about that testimony I'll talk to you about later on if we have time. But when the sea level didn't rise, Hansen was in his office with a reporter. And the reporter said to him, well, what's going to happen if we double CO2 from before the industrial age? And Hansen looked out his window and he said, you see that road? There'd be a lot more traffic on it. And this is almost a quote. And the reporter, his name was Reich, said, well, what do you mean? Well, Hansen said, well, the West Side Highway is going to be flooded. And the West Side Highway runs along the western edge of Manhattan Island. And then he said there'll be a lot more other problems. Well, it turns out he was predicting that for 2040. This is 1988. We've been 25 years into that period. The sea level in New York Harbor has risen less than 1 inch. It needed 10 feet to cover the West Side Highway. So Hansen, if his prediction comes true, is going to be looking for 9 feet 11 inches within the next 25 years to make his prediction come true. It is not going to happen. You can drive on the West Side Highway today very comfortably.
Tom, you have a lot of what appears to be compelling data, and it obviously is against the prevailing view. So my question is, have you gotten feedback from the mainstream people, or do they just ignore you? They
don't ignore me, but they did something like they did to my predecessor. I testified under oath at the New York City Council last year, around this time of year. And I complained that their proposal to reduce CO2, to reduce energy usage and measure it with CO2 reduction was incorrect. They were using the wrong measures. You can find my testimony on the internet. And like my predecessor, they put me last on the agenda when most of the city council people had already left the room. And my presentation on the inadequacy of the metrics is online. They all got a chance to see it. I offered them help in trying to make sure that they were measuring the right thing for the correct result. Nobody called.
Thank you very much, Thomas. I think we leave it at that stage.